What's going on, everyone? In today's video, we're going to go over slope-intercept form, also called gradient-intercept form, and why that is one of the easiest ways to go from a function written with numbers and variables into an actual graph. Let's take a look. All right, so when I'm doing gradient-intercept form, also known as slope-intercept form, depending on how you want to call it, they mean the same exact thing. You're dealing with this y equals mx plus c, sometimes called y equals mx plus b. And the reason that it's called slope-intercept form is because you're given the slope, m, and the intercept, the y-intercept, c or b. But either way, you have a slope, you have an intercept, and of course we have our x and y coordinates, but that's why it's called slope-intercept, because of slope and the intercept. So if we want to focus on the red line, which is this guy right here, let's go ahead and give me a red pen. I want to write out what the gradient is. So the slope, which is m, is going to be what? Well, again, all I need to do is pick out two nice points right here, and I can calculate the rise over run. In this case, I'm given a graph, so I can just count it. So I can go up 1, up 2, that's my rise. I can go over 1, 2, 3, that's my run. So my slope here, or my gradient, is 2/3. And what is my y-axis intercept? Right there, it's 2. And so knowing just those two easy to find pieces of information, I can go ahead and write the equation y equals 2/3 x plus 2. That's going to give me that equation. If you put it into a graphing calculator, you'll find that it equals the same thing. And if I now go to the purple line, let's see here, my purple line, my gradient. So if I start right here, I will go ahead and I will choose this point right here. That looks like a nice easy intersection. I'm going to go down 1, 2, 3, and I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8. So again, that was -1, -2, -3. That is my rise all over my run, which is 1, 2, 3, 4, 5, 6, 7, 8. So -3/8, that is written in simplest form. So that's going to be my slope. And now what is my y-axis intercept? Well, I can see from right here, it is 0, -7. So at -7. Give me the equation of -3/8 x minus 7. So in one case, I have a positive slope, meaning that as x increases, y is going to increase. And that's why you see this increasing as we move to the right. This is a negative slope, meaning as x gets greater, y gets less. And that's why we have it falling down. Okay, so let's go ahead and take a look at an example. All right, so we want to go ahead and draw these graphs. Let's say 5x plus 3y equals 12. I'll do this here in red. All we need to do is rearrange this so we have it as y equals mx plus c. And that y just means that we have a positive 1 as a coefficient, and technically also to the power of 1. So in this case, I have 5x plus 3y. I want to get y all by itself. I want to make it the subject. So let's go ahead and move that 5x over to the other side. So I'll have 3x is equal to 12 minus 5x. And now all I have to do is divide each side by 3. And I'm going to have a single y is equal to 12 over 3 minus 5/3 x. Let me go ahead and rearrange this. So I have -5/3 x over here, plus then 12 over 3 simplifies to 4. There we go. And so what I'm going to do now is I'm going to have my point 4. So let's go ahead and draw that right here, 4. And then my slope is going to be -5/3, meaning I'm going to have a rise of -5, 1, -2, -3, -4, -5, and then a run of 3. 1, 2, 3. I'm going to go to that point right there. And luckily I'm on an iPad, I can kind of connect these two just like this. But if you have a ruler, you should absolutely be using it. And there we go. It's that quick to solve. And let's have B, which is actually even easier. Let me go ahead and do this in purple. Y is equal to 1/3 x plus 4. So again, positive 4 is my intercept, and my rise is 1. And I'm going to go over 1, 2, 3 over here. And just like that, I am going to have this equation just like that. Good. And that's it. That is how you go from slope-intercept form, even if it's not actually given to us in this example, and go direct to a graph in honestly under 30 seconds. Okay, so these kind of questions really shouldn't take you a long time. And if you find that they are, all you need to do is practice, because I promise it'll make sense the more you do it. Okay, now let's take a look at a word problem and see what that looks like. So if we have two straight roads that have equations y equals 3x plus 15 and y equals -2x plus 5, we want to see, hey, a traffic light's got to be installed here at where these two roads intersect. It's going to be one of those probably speed cameras or checking a red light or something like that. And we want to find the coordinates of the point of intersection of the two roads to find out where this camera actually needs to be installed. So you can think of this as kind of like a city grid, kind of like a Google Map overlay. And we want to figure out how we can actually figure out where this point is in our in our city map. So there's a couple ways to do this. So sometimes you use substitution, sometimes you use process of elimination. But what I'm going to go ahead and do is I'm going to do it in two ways. The first way is algebraic by hand, and the second one is using my calculator. So if I'm going to go ahead and say, hey, y equals 3x plus 15 and y equals negative 2x plus 5. Again, these are points of intersection. And what that means is that the x coordinate and the y coordinate is going to be the exact same numbers, the exact same values, the exact same coordinates that satisfy both of these conditions. Another way of thinking about that is that all the x's and the y's are going to be equal to each other. So what this means is that if I'm going to have a point of intersection, if I have 3x plus 15 is equal to y, and then I have negative 2x plus 5 is equal to y, these are the same exact y's because they're points of intersection. So that means they have to be equal to each other. So I'm going to have 3x plus 15 is equal to negative 2x plus 5. And now all I have to do is solve for x. So let me move this negative 2x to the other side. That's going to give me 5x. Let me move 15 over to the other side. That's going to give me negative 10. Divide by 5. X is going to be equal to negative 2. And so now you'll find that if you put negative 2 in for x here, or if you put it here, you're going to come up to the exact same value because it's a point of intersection. That's one way you can check is by putting into both equations. So if I put into my first one, I'll have 3 negative 2 plus 15. So y is going to be equal to negative 6 plus 15, which means that y is equal to positive 9. And again, if I put in my other one, I'd have negative 2 times negative 2 plus 5. I'll have y is equal to positive 4 plus 5. I'll have y is equal to 9. So in any case, my point of intersection is at x coordinate, negative 2, comma 9. That is going to be the point of intersection at where this speed camera is going to be needed to be installed. Now, if you have a TI Inspire, keep following along because I'm going to show you a really nice way to do this in your graphing calculator. If you have a TI Inspire, go ahead and open up a graph page and go ahead and just graph both of these. So in this case, I have 3x plus 15, and I'm going to add a new one. If you're on the actual physical device, you'll hit the tab button, and I'll have negative 2x plus 5. Right? And then you're going to want to go ahead and find that point of intersection. Now this is where it gets really easy. All you need to do is hit menu, and what you're going to do is you're going to analyze the graph, and you're going to find the intersection. So lower bound means in the x direction, which one's my lowest. So I'll go ahead and put it over here. My upper bound is going to be on this side, right there. So I'm basically straddling this point of intersection, and you'll find that the intersection right here that the calculator spits out is negative 2, 9, the same exact answer that we found by hand. So if you're permitted to use a graphing calculator on your exam, go ahead and use this. If not, you know how to solve it by hand. So in any case, you'll be set. So now let's go ahead and solve a little bit a more complex problem, okay? So let's say there was a flower store named Bike and Bloom, and they're selling bouquets. And so we have a modeling equation now, which is giving us the cost in terms of the number of bouquets that it's making, okay? And we're using the Danish krone, the DKK, so it's a Danish company. So what we want to do right now, right off the bat, is find the gradient of the line representing this equation. Well, again, y equals mx plus c, right? So whatever is attached to our independent variable, in this case x, that's going to be our slope. So what we're going to find is that our value of m is going to be 72. So again, as a unit rate, what that means is that for every additional bouquet that's sold, they're going to be making 72 extra kroner. I actually just kind of gave the answer for number B, the meaning of this. What it means is that for the unit rate, it would be 72 over 1, right? So rise over run. So again, run is in the x direction, so it's going to be related to our input, our x, which is the number of bouquets, and 72 is our up and down, our y, which is related to the output, the cost. So what this means is that for every bouquet that they make, there's an increase of 72 Danish kroner. Sorry for my horrific handwriting. Right? That's all it means. So now let's determine what the y-intercept is. So again, the y-intercept in a linear equation is the one without any variables attached to it. In this case, 6,000. So my y-intercept is going to be 6,000. Now, could the total cost per month be 0 if no bouquets are made? Well, no, because if we made 0 bouquets, aka putting in a value of 0 in for x right here, Well, think about that. That would be 0 bouquets, so 72 goes away because 72 times 0 is just 0. But that's what this means in the modeling context, is that our y-intercept is actually going to be the cost that this company has to pay when they don't make any bouquets, which in this case is 6,000 Danish kroner. So that's what that means. So the answer is no, it can't. So if the total cost in a certain month is going to be 112,720 Danish kroner, we want to draw on the same axis the graph of the line representing 112,720 Danish kroner and the equation modeling the total cost C. So that's a really complicated way of saying draw out a line that represents 112,720 and then just go ahead and sketch onto it the cost function, 6,000 plus 72x. So again, this is a sketch, and you can use whatever resources you would like for this. But for me, I know that my cost, I'm going to go ahead and call this point my 112,720. And I'm just going to draw a straight line. Because what that means is that no matter how many bouquets I'm taking into account in this scenario, the cost no matter what is going to be 270. Sorry. So now what we want to do is have the equation modeling the total cost. So I know that this cost function is going to start off at 6,000. And again, this is just a sketch. It doesn't need to be super precise. And I know that my slope is going to be 72 over 1. And if you wanted to go ahead and do that into a calculator or get some values, but you know that it's going to be going up in this general direction. I already kind of know the context behind this, so I wouldn't say I'm cheating, but got a little bit of a head start. But that's exactly what you're going to find. And what you want is you want to find the number of bouquets made if the cost is 112,720. So what you're asking for is, hey, what is this point of intersection right here? Because the reason why we drew that line is so that way we can find the point of intersection, whether it be algebraically by hand or in a graphing calculator. What is that actual number? That point of intersection is going to tell us, hey, it is when this cost function is going to give us the y-coordinate of 112,720, and what would be the number of those bouquets? So I would have the bouquets down here on my x, and I would have my cost up here on my y. So what is that? Well, again, you can use the calculator method that we already covered, or we can do it by hand. Because I know that my cost function is 6,000 plus 72x. And I want to know when that is equal to this cost I'm looking for, 720. Maybe that's like the maximum they have in their budget. They want to make sure that they're not going over that. So if I went ahead and simplified this down, you can go ahead and do it by hand. But we would end up with a rounded number would be 1,482 bouquets is equal to that number of x. So that means is that at 1,482 bouquets, they're a little bit under that cost of 112,270. Any bouquet above that, they are now going to be above this price. So I can actually go ahead and draw this line down to the number of bouquets. That would be 1,482 bouquets. That would relate to this cost right here, as close as possible, because bouquets have to be a whole number. You can't sell fractions of bouquets. Of 112,720 Danish kroners. So again, it's the same exact idea. You can do it in a calculator or you can do it by hand, but it's going to give you the answer that you're looking for, which in this case for modeling is the number of bouquets that is going to give us the cost that we are looking for. Okay, so just a little bit of context added onto it. I hope that shed a little bit of light into how linear equations and slopes and slope-intercept form can be used in not only graph functions, but also be used in modeling and how we can use those equations to find out problems, particularly in this example, the number of bouquets a company is making given a cost restraint. Okay, so I hope that helps, and I'll see you all in the next video.